Hi, everyone. Thank you very much for coming. I'm Dan Rosenheck. I'm the data editor and sports editor at The Economist, and I'm here to talk to you about EAGLE, the Economist Advantage in Golf Likelihood Estimator, which is a backronym for a statistical prediction system for golf tournaments. Yes, it works. Great. What is EAGLE? EAGLE is a live win probability prediction model for men's major golf tournaments that is hosted on the Economist website. From the first tee off to the final hole out, it simulates results 10,000 times for every hole by every player that has not yet been completed and repeats this every 2 minutes. It then counts up all the simulations and sees what share of the time each player wins. It basically works. If you look historically at every player that EAGLE has had a prediction for at every point in a tournament, its estimated win probability and how the share of the time they actually went on to win, you get this very close match. So it works. So a little timeline of EAGLE's history. It launched rather quietly on our website in the summer of 2016. It got a bit of attention from the golf press. And 2 years ago, I gave a talk here summarizing the basics of the methodology. However, forecasts of live win probability models like EAGLE are still not widely reported during golf tournaments. In part, that is because EAGLE hasn't really been offering a lot for people to look at. There's a lot of work going on behind the scenes, but the only thing you can actually see on our website so far is this rather drab table. Fortunately, 2019 will mark a whole new world for my little project. In time for the Masters in April, we will launch an interactive visualization that will let you dive into every forecast. You'll be able to see win probability over time by player, each player's chance of each score on each hole, and how that changes over time, the model's estimate of whether they've gotten better or worse has changed since the start of the tournament, predicted leaderboards, who's likely to gain, who's likely to lose, the whole enchilada. The idea is that you're watching on TV and you've got EAGLE on your phone alongside it, and you're smarter than whoever you're watching it with. The launch of this new front end will coincide with the debut of a fundamental revision to EAGLE's internal math. We have tweaked it so it now uses an explicitly Bayesian framework where you start each round with a prior expectation for how the course, the hole, and the player will impact each score, and then it updates those to a new shape distribution as the results come in. So hopefully now that we have this visualization, more people will be curious to learn what this thing does, whether it works, whether it's any good. So I'll offer you a quick survey of how EAGLE works and what's changed and what's new. Oops. So sports are often complicated. Anybody who watches football is aware of that. Golf, less so. One of the biggest challenges in sports modeling is determining how much of one side's success was caused by them playing well versus how much was caused by the other guys playing badly. And if you have a team sport, then you have to allocate that further among other players. In golf, you got to ignore all of that. Another problem that you have in modeling other sports is lack of data. In the NFL, you only have 16 games a year, so it's perfectly normal for a not that great team to go 8-8. In golf, every player typically plays 1,500, 2,000 holes a year. So you're very data rich. Finally, in many other sports, there's lots of complexity as far as how the different constituent events in the game, like a hit or a walk in baseball, add up or don't add up into runs. Whereas in golf, a stroke is a stroke is a stroke. Sorry. Now, simple doesn't mean it's necessarily easy to predict. Golf scores are obviously extremely variable, and players have really good rounds and really bad rounds all the time, and there's no way you can see that coming in advance. Sorry about that. So although golf tournaments can seem to take quite a long time, each player usually takes about 18 hours to get through their 4 rounds. 72 holes actually isn't nearly enough to smooth out all the randomness that you see in golf scores. If you compare it to tennis, a typical golfer will play 72 holes over the course of a tournament. The guy who wins Wimbledon will play 1,600 points. So as a result of that, there's hugely more variance in golf the best player going into a tennis tournament typically is given by betting markets around a 35% chance to win. In golf, it might be 8. So when people ask me, well, did Eagle get it right? The answer is no. I thought that the guy that won, only had a 95% chance to lose. So, interpreting probabilistic models can be tricky, but you just want the test is when you say something is a 15% outcome, it's not 5% and it's not 50%. Sorry about this. However, when you zoom out to longer time periods than just a single tournament, you start to see patterns. A typical golfer will play about 100 rounds a year, and the bulk of their scores will cluster around the level that's most reflective of their true ability. For the average player in a major, that's about 2 over par per round, with some spread around that. However, there is, of course, a lot of variance. Sometimes you have a really bad player who will just catch lightning and post the best score in a round, and sometimes you have elite players who nonetheless will just not have it on any given day. So every player's distribution of round scores looks slightly different, but there tend to be predictable patterns based on their skill and profile. So the best players in the world, Dustin Johnson, Justin Rose, and this era, Brooks Koepka, their most likely result is par. So par is it's kind of a misnomer. It's not the level that you should be expected to get. It's the level that the best player in the world will get. And elite players will typically be between 6 under and 6 over 95% of the time. And if you look at these the two curves on the left, the furthest left-hand one being Tiger Woods at the peak of his powers, the middle one being Dustin Johnson, so an elite player today, they tend to follow these very nice normal distributions of round scores that just can be offset by whether they're merely excellent or the best player ever. By contrast, fringy players tend to be about 4 or 5 strokes worse per round overall, but also there's a lot more variance. They can still, manage to sneak under par for a day, but when they do badly, they do really badly. And so to accurately model those kinds of tendencies, you need something that can handle that kind of non-normality. So I use something called the skew-T distribution that allows things to sort of lopside and stretch out to account for that complexity. So with those kinds of distributions, you could already do a pretty decent job of predicting and simulating golf tournaments. The first step would just be to fit one of these skew-T distributions to each player's history of round scores. You will typically get the best results by factoring in when a previous round occurred. So each round loses about a little less than 2% of its predictive power every week. And then even for players of a similar estimated skill, you often have variance in how much data you have about them. So to take here, you have 2 guys, Thomas Pieters and Young-Han Song, who the model thinks, at least at this point in time, were roughly similar in skill, but Song played every single week and Pieters didn't. So Eagle has more confidence and therefore a tighter distribution around Song's scores than it does around Pieters. So Pieters it'll simulate more randomly good and bad days just because it knows less about him. So that would be step 1, to fit one of those distributions. After that, if you want to simulate a tournament, you would just take 2 random draws from that distribution for each player. You'd call that your first 2 round scores. Then you would add them up, apply the cut rule, see who gets to the second half of the tournament. Then for those who get to the second half, simulate 2 more, add them up, and see take whoever the lowest score, declare that person the winner. Hopefully there's not a tie, because you'd have to figure out what to do about playoffs, flip a coin. But then if you just did that 10,000 times and counted up how often each player won and divided by the total, you would get win probabilities. That is not all there is to it. Although those win probabilities would actually probably be pretty reliable, they wouldn't be that useful, because if you're only working at the round level, you would only get to update your forecast once play has finished for the day and everybody's already gone home, which isn't a great way to retain an audience. So you need to move beyond that, just like I need to move to the next slide. What we really need is to drill right down to the hole level. If we could simulate scores on each hole, then we could give users a companion to their viewing throughout the day. But Drilling down to that level requires a lot more complexity and challenges. So the first, when Eagle was born, it fit whole scores using what's called a cumulative logistic regression, which is a sort of disarmingly simple approach. It starts at one level, here at the bottom, and says, okay, binary question, yes, no. Did you get better than an eagle? Worse than an eagle. If not, then you got an eagle. What's the chance of that? 1%. Okay, 99% you didn't get an eagle. Did you get worse than a birdie? Okay, well, 87% of those chances are yes, 13 are no. And so you just cascade down the decision tree and add it up, and what you wind up with are probabilities that add up to 1. However, these cumulative logits can be very badly behaved. They're fine when you have a huge amount of data on every score level, but there's no guarantee that it's going to be unimodal, that it's going to slope up to a peak and then back down. And when you and for extreme situations, a really bad player on a really tough hole, these things can go totally haywire, and you can have the chance of an 8 being higher than the chance of a 7. So for those kinds of, if you want to model those kinds of extreme situations properly, then you need to somehow impose a shape on the data, a structure. So for that, you would need a parametric distribution where there's some just simple mathematical function that's going to fit everything. So what are some parametric distributions? The most familiar one for discrete data, count data, like the number of shots, is what's called the Poisson distribution. But it turned out that the Poisson does an absolutely god-awful job of fitting golf scores. If you take a look at just this chart here, you can see the blue is the frequency of each score on par 3s, and the orange is what Poisson thinks it should be. So Poisson thinks scores should be vastly spread out, and you should be seeing holes in one, 1 out of every 7 times. In fact, 2/3 of the shots are par. So clearly, the Poisson is not the way to go. So, if it wasn't going to be the Poisson, what was it? Well, I shopped around for a bunch of other discrete distributions that might provide a better fit for this data. I tried the negative binomial and a Delaport and a bunch of other things you've never heard of. But all of these things work best for over-dispersed data that are more spread out than a Poisson. The golf data is less spread out, so that was proving really tough. Finally, I got desperate. And this is actually what I did. I went to Google, and I typed in 3-parameter discrete distribution and hit enter, just like that. And what I got was this random paper in this medical journal I'd never heard of from some guy in Kashmir announcing some discrete distribution that he had discovered or invented or something that apparently claimed to be able to fit under dispersed data. So, I copied down the probability mass function from this paper, put it in Excel, open solver, typed in that equation on those tablets, hit fit, and bam. Every single score was an absolute perfect match for all 3 par values. You can see the blue is the real frequency, the orange is the terrible Poisson, and the gray is this discrete Burr type 12 that just nails it. The discrete Burr is incredibly flexible. You can not only fit expected distributions based on knowledge before a hole is played, but even after. You can let a model say, okay, I know what score you got for this round. Now tell me what the probability we would expect to see on each hole is. So in something like this, I seem to have lost one of the 2 distributions, but it doesn't matter. You can see here, so this is a really bad player, Michael Fry, who having a really bad day on the hardest par 5. And you can see it thinks there's about a 30% chance of a 6, a 30% chance of a 7, still has a decent chance to get par, almost certain he didn't birdie it. No matter what the whole permutation, player skill, the discrete Burr can handle it. It's pretty straightforward. So in the same way that you could simulate tournaments at the round level using those SKUTs, you could simulate them at the hole level using these discrete Burrs. You could just fit one for every player on every hole, take 10,000 draws from each one, add them all up, and see how often each player wins. You could even update during the course of the day by saying, okay, here's the discrete burr based not just on what I knew before the day, but in this simulation, I simulated you for 3 eagles in a row, so now I think you're a little better than you used to be, and you could adjust it that way. Nonetheless, that method, although it would probably be decent, it still makes a really big assumption that the data might not bear out, which is I, D. So even if you do that kind of dynamic updating, you're still only allowing for a very weak hole-to-hole correlation in how golfers do on any given day. Maybe the world works like that. Maybe golfers are just robots, spitting out coin flips. But maybe they're not. Maybe they're people. And maybe they actually, have good days and bad days. I mean, is this a thing? Maybe, just maybe, golfers could even display a hot hand. So to allow for the possibility of that kind of correlation between holes, we need to break down that round-around variance we see into 4 elements. The first is what I call a course day effect. All scores by all players on a given day, we're going to shift our expectation up or down by a given amount. That could be because the weather's good or bad, the greens are firm or soft, something like that. You can get huge variance within the same tournament in this stuff. In the US Open this year, the first round, the average score was 76.5. The final round was 72. That's a giant difference. So you've got a distribution of these course day effects that you can draw from. Next, we have a hole day effect, which moves up or down the expected score for all players on a given hole by a certain amount. So that can happen if the groundskeepers move the pin or the tee or something like that, or just weather affects some hole differently. You can have the average score on one hole move by vast amounts within a tournament. So you can fit a distribution to that and model it. You've got a player day effect. This is the theoretical hot hand or choker effect if it exists, that says, rather than simulating each hole by each player IID, I'm going to say, okay, in simulation 1464, you're going to have a terrible day. And in simulation 1919, you're going to have a great day. And that's a uniform effect for all holes for that player on that day in that simulation. So, if there is a momentum or hot hand thing, if you were watching the 2017 British Open and you saw Jordan Spieth, hit the ball behind that TV truck and somehow save it, and he's down by a stroke, but you're just like, he's going to pull this out. Maybe that's BS, but we should at least give the computer the option of determining that it's not. And then finally, you have the ultimate IID coin flips. Nonetheless, despite all this correlated stuff, it is still a game of inches or millimeters, and crazy stuff happens or doesn't happen all the time. And sometimes the ball sits on the lip of the hole for 12 seconds and then drops. And that you do just want to model as a series of coin flips. So, to disentangle these 4 effects, I had to resort to STAN, which is a probabilistic programming language that's built to run MCMC models. So what MCMC allows you to do is to combine all these effects into one hierarchical model, where we say, okay, for any given player, on any given hole, on any given day, we're going to start with a prior distribution of here's what the course day effect could be, here's what the hole day effect could be, here's what the player day effect could be. I'm going to pull one value at random from each of those distributions and add them together and say, okay, Justin Thomas, simulation 4912 on hole 16, these random day effects come out to shift him up by 0.1 strokes per hole. Then it takes those randomly simulated values and will feed them into a series of equations that take everything else we know about the player in the hole. So he's generally really good. It's a short par 3. It's been playing hard in the past, and you've got 0.1 strokes per day of these random effects. Each of those variables is going to get a coefficient for each of the 3 parameters of the discrete burr. Then, once you fit those equations, you can just feed those resulting 3 numbers, mu, sigma, and nu, into that probability equation, and you will get a resulting distribution that you can then take these IID draws from. So then how does Stan fit this? Instead of doing that just once, it does it thousands of times, and it finds what values for all of these coefficients, the size of the player day effect, the spread, how it's affected by the past, whatever, what values for all these coefficients will maximize the probability that through this coin flipping random process, we could produce data that is actually the data that happened in real life. And if you do just 100 of those draws, as you can see, you're going to get only a weak fit to the kind of distribution you look for. If you take 50,000, you're pretty much going to nail it. So then finally, as the day goes on, Eagle's going to update those priors. When the day starts, they're all at 0. But now we're halfway through the day, and we can see, for example, on say this is a whole day effect, that it started centered on 0, but now if you look at the red line, there's been a huge range of scores, but they're tending to come in above expected. So for the holes we simulate on the rest of that day, what's called our posterior distribution, now we're going to simulate that whole day effect from a distribution that is both shifted to the right, as in it's harder, and it's a narrower range because we have more confidence because we've seen already some of these holes already. So to wrap up, the way that would look in practice is you would say, let's take you've got this distribution of scores. This is where we started the day with. Now, it's coming in wrong. All the score, we're seeing a lot more birdies than expected, a lot fewer bogeys. So now we're going to update to a posterior that blends all this information into one beautiful whole. Okay, so that's all she wrote. Thank you very much for your interest, and I look forward to your questions.
Couple minutes for questions. Right here.
So a potential fifth IID factor is motivation. So like a player on Thursday, he might be 6 shots off the cut line, projected cut line, and he really has to like gamble on Friday to try and make it, or he's 7 shots off the lead on Sunday, he's going to be more aggressive. It sounds like that's not part of what you're doing now. Is that because of anecdotal thoughts, or have you done any analysis on that?
No, that is definitely a good point, whether golfers play strategically. I have thought about it. I would love to test it. I would love to incorporate it. I haven't gotten to it. Talk to me next year. I'll see if I can do it, because you would think it would matter.
How difficult was it to write code and fit parameters for a model or a type of model that you probably hadn't seen before, and that there's not like a lot of existing packages for? You know, when I think of modeling, you think normals and gammas and stuff that you can probably sort of automate pretty easily. How hard was it to sort of pick this sort of weird distribution and roll with it?
Glad you asked. I hadn't touched calculus since high school. And I mean, the probability mass function I found on that paper was simple enough. But to actually, I mean, in Stan it's easier, but to get it to fit in a different way using R, you need to complete a full Hessian matrix of cross derivatives and partial second derivative. It was, I asked for a bunch of help, and a few people saved me. I wouldn't recommend trying it at home. But fortunately, now that I'm like the great evangelist for this random discrete Burr package, discrete Burr distribution, I've asked some R developers to get it into their packages, which some of them have done. So no one will have to retrace my miserable footsteps.
I think we have time for one more.
So your model obviously fits the data super closely. Are you concerned at all about overfitting for specific holes or specific, I mean, whole day effects? I can imagine that I don't know, I'd be a little concerned about overfitting. I'd wonder if you have to deal with that in this setting.
So, I mean, I do model selection. So I regularize everything, basically using elastic nets. I can drop variables, so I try to keep it parsimonious. But the other thing is that I would be super worried about overfitting using something like that cumulative logit, where it can go, totally haywire in extreme situations. But with the discrete Burr, there's only 3 parameters. You're imposing a shape on this data that fits your prior of, what a well-behaved golf score should look like. And there's only so many ways it can move around. And so, in those kind of whole day effects, it's the strength of the Bayesian approach as well, that it's drawing from some distribution every time, and so if it has low confidence in a parameter, then there's going to be a very wide standard deviation on that prior, and so hopefully it will then, and therefore you're going to get a low log likelihood on the result, and so basically the fitting process is going to chuck out or really scrunch down the impact of uninformative variables for you.
That's all we have time for. Let's give it a round of applause for Dan.